Are you talking about chicken?
Yeah.
What?
They were so salty and so oilful. I feel headache now.
Did you say oilful?
Yeah, and
Cute.
And too salty. Too salty. Headache.
It's not oilful. What is it? Oily.
Oily?
Yeah. I do like oilful though.
Oilful.
And if it's not much oil, it can be oil-less.
Oilful.
Yeah.
Oilful makes sense.
I understand.
Oilful.
I understand. Yeah. What?
Did you say awful or oilful?
Oil.
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 O-I-L.
Oh, I thought you said awful.
No, that would make sense. Well, it probably was awful.
Yeah.
If it was oilful, it's also awful, I would
So
say
you are
so.
telling him it's olive. If he was saying awful.
No. If he's saying oilful.
I said
Oil.
oilful. Oilful.
Oilful.
Oilful.
Oil.
Awful. You mean awful.
Yeah. Yeah. Her listening's not so good. Okay. Application of radioactive isotopes.
Application.
Yes.
Radioactive isotope.
So this Friday we have class.
We'll do physics class. Actually, we'll have to do a tutorial on the stuff we've done. Although we did one, so the only tutorial would be on the one we just did,
Yeah.
which is for babies.
Yeah. Baby.
It's just a graph.
Yeah. City.
2 weeks to finish the coursework?
2 weeks from yesterday.
Not exactly yesterday.
Yeah, so 2 weeks from yesterday would include a weekend.
Yeah.
Yeah. But maybe I'll make it 2 weeks from today. Because I got emails yesterday, but I wasn't here to read them, so maybe I'll be generous and make it 2 weeks from today. Or 2 weeks from tomorrow.
Oh, you're so nice.
Or too nice. Right, application of radioactive isotopes. So this lesson here is all just about how we can actually use radiation for good instead of evil. Okay. So the first one, or the first thing to say, radiation is not all bad. Yes, it's bad for your health, but it actually has some applications which are useful. Please note the ones in bold are extra important for the exam, which is the first one here, which is the smoke alarm. Now, you don't need to write this text down, it's the picture I really care about explaining here. So, smoke alarm, there's one up there, okay? How does this work? So, you can't quite see it in the picture, but I'll explain. What you have here is something radioactive, okay? And the radiation then is inside the smoke alarm, and it's in between two plates, a positive and a negative. Now, what happens is when the smoke alarm fills up with smoke, this actually, it gets in the way of the alpha particles. Because remember we said alpha is very easily blocked. What can block an alpha particle? Skin, piece of paper. So a smoke particle, a particle of smoke that's quite big, quite heavy, quite dirty, that can easily block an alpha particle. So here, what charge is alpha?
Plus.
It's plus, isn't it? So it will go to this plate.
Yeah.
But when this fills up with smoke, this plate gets less alpha, which means you have less current. So when the current drops, that's when the alarm goes off. Okay? This is how a smoke alarm works. So one type is to detect smoke. This is called an ionization chamber. Smoke detectors are the most popular because they're inexpensive and are sensitive to a wide range of fire conditions and other types. So anyways, there's a lot here. You don't need to write it all down. I think for the exam, it says, describe the use of radioactive isotopes in smoke alarms. So for the exam, you don't even need to know how it works. You just need to know
What is it?
Well, describe the use of radioactive isotopes in, yeah. English time. Describe the use.
Describe.
Oh,
Yeah, but it doesn't describe the use. Weird. I'll have to ask an EAP teacher this. Anyway, what you can do is just copy the picture, and I'll draw the picture again for you here. Okay. So you have power supply. This one here is positive. This one here is negative. This here is an ammeter. Okay, and here you have some alpha, and the alpha fills this up. Okay, and then what happens is some smoke comes in here. Now, what happens when the alpha hits the smoke? It will ionize the smoke. So what happens when something is ionized? What does it release? Electrons, thank you, yeah. So, just to be really clear, before the smoke hits, the alpha is just going through like this. And yes, some of it will hit the negative plate, okay? But when the smoke fills it up, the electron is freed, and the electron hits this plate here, and this affects the current. This reduces the current. So it reduces the current because you get an electron here, and also there's less positive ones here. Anyways, the long story short is the current, the I decreases. And then when the I decreases, then you get the alarm. And this is the smoke.
the smoke ionizer?
Yeah, I think so, because now I don't even think you need to say that in the exam. I think it's actually enough to say something simple like the smoke interrupts the circuit. But I think the mechanism is that it ionizes and releases an electron.
Aluminium 21.
Oh yeah, and the other thing you need to know is what is the source for the alpha. So the material that's inside the smoke alarm is this radioactive material, Americurium-241. And it has a half-life of 400 years. Well, it just means the smoke alarm will be gone before the material's half-life is used up. 400 years. But you realise, of course, other parts of the smoke alarm will fail before 400 years. You know, like the metal in the circuit will, what's the word, oxidize, corrode. Yeah. This, yeah.
But it looks like work backward. To get alarm, you need more current.
To get what?
To get alarm.
No. We didn't talk about this because it's not on the course. But they use something here called a NOT circuit. So a NOT gate means no current alarm on and current alarm off. This is called a NOT gate. But we don't study this. But I understand what you mean. That current means alarm, but it's actually the opposite here. Yeah.
What if it just is electron and the current decreases?
Say again?
What if it turns into an electron while the current decreases?
Let me think. Well, maybe I have it wrong. I'm sorry. When an electron attaches to something with a positive charge, if something is positively charged and you stick an electron on it, do you not reduce the charge? Like if you have something with a positive charge.
I thought they were like the electron will travel through the circuit.
I don't know. I think I've gone into too much details. Details I've not thought about, perhaps. But if it's a positive plate and the electron hits the positive plate, does that not reduce the charge of the plate? But don't charges,
Oh, yeah. Even the charge moves.
yeah,
It's boom, 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 like this.
yeah.
Boom.
It's you don't need to get it because it's not on the syllabus. I've already said more than I should have. I should have kept my mouth closed. If you're curious, you can YouTube how smoke alarms work and get a beautiful video of how it works. But for the exam, I've given you more than what you need.
If you get it, let me know that.
All right.
I'm curious too.
So, in this room, there's at least one radioactive source in the smoke alarm.
That's the problem. I feel headache
Yes,
because of that.
yes, yes.
Headache.
Or maybe it's making you smarter,
Isn't it? I don't know.
like an X-Man.
I'm not. I'm not smart.
I don't know, but the radiation will help, give you superpowers. Yeah. Okay, so if you have a smoke alarm, there is radioactive material inside of it. Yeah. It's only harmful if you do something stupid like open it and eat it. Otherwise, it's safe. Yeah. And it's a small amount, like 1 gram radioactive material. Okay.
Is this Mary?
Mhm. Yeah. It's okay? Yeah? Okay. Yeah.
Is that capacitor or plate?
In fact, capacitors and plates, they're the same. They look the same, don't they? The only difference between capacitors and, well, there's not really much of a difference. It technically is a plate, it's an electric field. But if you put 2 plates close together and put it in a vacuum, you can make it a capacitor. Yeah. But I suppose it's more of 2 plates than a capacitor. Yeah. Okay. Continue. Yeah? Yeah, you got this, Bruce? Alright. Next example. This one here is a good one. When you have a water leak, okay, so you have a town and the water's leaking under the ground and you can't see where the water is, what do? Well, they put this radioactive material into the drinking water. And yes, and when it leaks out underground, what happens to the ground here? It becomes radioactive. So when he walks along with his Geiger counter, and when his Geiger counter goes click, 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 it means he found the radioactive ground, which means he found where the leak is. Of course, it means the people are drinking radioactive water.
So we can use the thing in the fire right now.
It uses a different one because you want to have something with a short half-life because you want it quickly to decay. So this fluorine 18 has a half-life of 2 hours, which means after 24 hours it's become safe again. Because that's 12 half-lives, so that's long enough.
Is it similar things with the finder the bomb blood?
Yeah, except instead of looking for metal, you're looking for radioactive ground. Okay, so you don't need to draw this picture, but you need to write something down to explain what's happening here.
To find the point of leak
Yeah,
with
the leaks.
fluorine 18.
Yeah.
Leaks-
Bruce,
leaks
are you writing this down?
Leaks point?
Ah, Bruce, write a sentence. What's he doing here? What's he doing? Not metal. Leak, where the water's leaking out.
Find the leak.
What's it called?
Tracer?
Yeah,
Tracer?
just like the video game character.
To find the leak spot. With the fluorine.
Okay, you got that? So you want to use a half-life that's quite short because you don't want people drinking the water that's radioactive. It's not really good for you. Yeah. Unfortunately, when radiation was first discovered about 110 years ago, people thought it was good for your health. So you could buy water with radioactive helium in it. The water would glow when you turned the light off because it's radioactive, and people thought this meant it was healthy and full of energy. Instead, they were killing themselves by drinking it. So you don't really want to do this.
They should have met you.
Yeah, well, we know it's dangerous now. This one here is used in the hospital. Technetium 99M. So what they do here is they give the patient something to drink, and it fills up their muscles and their fat and their skin and their tissue. So their whole body becomes radioactive. Now, why might they do this? Why can't they just use an X-ray? Why would you do this instead of an X-ray? What do you think?
X-ray is... X-ray...
Yeah, but what's the advantage of this instead of an X-ray? Yes, because what can X-rays show you?
X-ray is just like bone.
Yeah. X-ray is just for bones.
Yeah.
But maybe there's something wrong with the person's lung or liver. You can't look at this in an X-ray. Okay? So you can do something like this. So you can see this patient, I'd say something, well, maybe there's something wrong with his liver. There's lots of spots here. But it's actually interesting to see the parts that are dark, because the parts that are dark means they have more radiation. Now, why are these two parts of him dark here?
He was up there.
Huh?
He was up.
No. This is on the neck.
Lymph.
Yeah, lymph nodes, yeah. The body is trying to clean the radiation out, so the radiation is collecting up here. This lymph nodes is used for removing stuff, isn't it? And there's some under your arms as well, which is why these are here. And of course, the liver and pancreas and these things, they're organs for filtration as well, and so on.
Heart is here, was it?
On the left.
Left, right?
Correct, yes. Yeah. So anyways, this material is kind of like used for finding any problems with skin, muscle, tissue, organs, non-bones, things which aren't bones.
Should we learn their name?
For the exam, the only name you need to know is the first one we've done. But it's at least good to see its name, because in the future you might see it again. Yeah. I don't know what the N is for. Like the 99 is obviously for the weight, but I'm not sure what the M is for. If it's some kind of modified version, I'm not sure. I'd have to look it up. Again, would we want a long or a short half-life here?
Sure.
Why?
This is
It's radioactive in your body, in your whole body.
Yeah.
So 2 hours would mean after 24 hours he has peed it all away, and it should be safe then. Yeah. Okay. So if you can write something down about this one.
Fine.
Has anybody had this done in the hospital? They give you a drink and find the broken heart.
Organism problem. Organism.
Also, another problem with this guy is I think he could lose a little bit of weight. Might help him out a bit. No, if we're being a doctor, a professional now,
How does it go into or is it the blue?
I think the redder it is, the more radioactive. So maybe blue means no radiation. So you can see here, like, your arm isn't really connected to your organs,
In the head, like green, like around the brain.
I think what's happened is the tissue maybe around the brain has become radioactive, but I think the brain is still pretty blue here because maybe it's more isolated to the rest of the system. Just like the arm is blue because the arm doesn't really have any business with the lungs or, Like you can really see the stuff that has a job in trying to clear out poisons from the body is where all the radiation is. Yeah. Is this one okay? Yeah. You get the idea for this? Yeah. Okay. Can I go to the next application? Yeah. 30 million procedures per year. That's a lot. This one here, this is used for security. It's used, like for example, at the airport. They use this to, they use the radiation to scan to scan objects. So what happens is you have your radioactive material, in this case cobalt-60. It might be something like this, okay, cobalt-60, and you point it at something like somebody's bag, for example, and the cobalt releases, I believe, gamma radiation, or beta and gamma. So the radiation comes out, goes through the bag, and then you have some computer will detect the radiation on the screen and turns it into an image, like that. Now, why don't they use X-rays? Well, the problem with X-rays is, if you've got like something made of paper, the X-ray will just go through it. Like, the only thing that would show up on an X-ray is something really, really hard, like bone. But maybe it's not something really hard you're looking for. Like in this one here, this metal gun. I don't know if you could see that in an X-ray, because I don't know if the metal is, I'd say it maybe is thick enough, but maybe not, for an X-ray to work. Okay, so the cobalt-60 is good for when you want like a weak X-ray, something that can kind of get more details. Okay, the disadvantage of cobalt-60 is if you have a really, really thick wall, then it doesn't work, because it can block it, okay? So the situations where you use this is when the wall is not so thick, just like at the airport with your bag, it's not so thick. Or here, you know these army truck, it's only a canopy, it's only fabric around the truck, you know. So this works well when the material on the outside is just like a fabric, okay. So the cobalt-60 is used for security. It's like an X-ray of bags and trucks and things like this.
How thick is it to block a gamma ray?
Gamma ray needs to be pretty thick. So I think actually it's mostly beta and some gamma.
So it's like I smuggle drugs and I put it in like a very thick box and then I put it in my bag.
Very thick?
Yeah.
Like it would need...
like how thick is it?
If you want to smuggle drugs, how thick will your drug box need to be?
I think if they find something thick enough, they check it.
Yeah, I think, like if something's going through the airport scanner and there's a big solid block that they can't scan, like this big.
Like you make it shaped like a t-shirt or something.
A solid t-shirt that they can't scan. I think that'd be suspicious. No, I think it would need to be pretty thick, like maybe like if you want to block something at the airport, you might have to use 2 to 3 centimeters of lead. That should block it. Of lead. Yeah, are you making notes of this? Yeah.
Why do they let us remove our laptop?
I think it's so they can get a clearer image of the laptop, because if your laptop is in the bag, like a laptop bag, and there's things in the bag like chargers and other things too, then it can make it difficult to see if there's anything in the laptop. So I think you just get a clearer image of the laptop.
But like, if normal people just smuggle drug without like any box and just put it in their bag, like how can they detect it?
Sniffer dogs.
Not all airports have those.
I know, so that's how drugs get into countries. So if you're willing to take a chance, then, you know. Yeah. Anyway, just because you don't see the sniffer dogs doesn't mean that they don't use sniffer dogs, because as far as you know, they could have sniffer dogs checking the luggage before it goes on the plane. in an area you don't see, you know. But I mean, take the chance if you want. Next trip back to Malaysia. Okay, did you write this down now? So cobalt 60 is good for security. Yeah, are you two hatching a plan over there?
No, Malaysia one if you get caught, it's a death penalty.
Yes, I know. Yes. Yeah. So I don't.
Definitely.
It's dangerous. Okay.
Yeah, no shit.
Is it death penalty? Is it death penalty?
Yeah.
For drug?
Yep.
Oh my god.
Drug smuggling.
Oh. Is it
In the country or out of the country?
Both?
Both. Okay.
both?
Is it what? I thought you transport drugs.
Transport. Okay. Okay.
Death
But
penalty?
if it's in transport.
Right. So did you write that down? Cobalt 60 is used for security at airports or military. If you want to smuggle drugs, you must use at least 2 to 3 centimeters of lead. Okay, all right, good. Continuing now with our next application.
Is there more?
No.
Fighting cancer.
Yes, yes. This one I think is the most, for me, it's the most interesting one application. Using something called boron 10, which is stable, not radioactive, which is stable, and neutrons. This one I think is very, very interesting what they do here. I'll need to draw a little picture to show you, okay?
Oh.
Yeah, now let me explain. Okay, so this is how it works. Right, so here's our patient. And there's their body.
You're a patient.
Yeah, there's the patient there now. Okay, I know it looks like a plane as well, but I'll put a smile on there. Now, this is how normal radiation therapy works for treating cancer. So let's say they have some cancer here. The machine that they normally use is like this, like a big dome. Now, they can't put all the radiation in one spot because that would actually damage the skin above where the cancer cells are growing. So what they do is they send it in many different directions. So one little spot maybe gets a little damaged and this little spot gets a little damaged. But all of these meet in this location. And this is how they destroy it. But the problem with this method is you're damaging healthy skin as well, and you have to be very precise. But what I think is interesting is this method where they put here boron 10. Now boron 10 is stable. It's not radioactive. There's no radiation coming out of it. Okay, none. And then what they do is they fire neutrons. And the neutrons aren't radioactive, you know, they don't really hurt you, they just get fired at the boron 10. But when the neutron hits the boron 10, the boron 10 becomes boron 11. Boron 11 is radioactive, and it has a half-life of a nanosecond. So basically, you've got, if we picture it like this, this is the cancer. So inside the cancer, you put in your boron 10, and then you fire the neutron at it. And the neutron goes into the cancer, and it turns the boron 10 into boron 11. So it's like it explodes, because it has a half-life of a nanosecond. So it becomes radioactive, and it destroys the cancer from the inside. Whereas the old treatment destroys it from the outside. It fires radiation at it, and it tries to destroy it from the outside, whereas this one destroys it from the inside. So, you know, it's very different, much better approach. Okay? So, I think this is very interesting. If you were ever to look up more about it, boron 10.
Do we eat
Yeah.
the boron?
I think they inject it into the site, so they can fill it up, you know? Alright, so write this one down. Yeah?
Is it painful when it explodes?
I might have been a bit dramatic when I said explode. It's more like just it destroys the cancer. Explosion is too dramatic, sorry. It's not like it's going, you know.
Are they unconscious when you do that?
I don't know actually. I don't think they have to be unconscious, but they do have to be kept stationary.
Can we choose to be unconscious too? Like, even if you don't have to, can we choose to?
I don't know. You might be able to. You might be able to, yeah. I think so. Okay, you got this? You got this, guys?
Yeah.
Yeah. Okay, next one. Back to cobalt 60 again. Another application of cobalt 60, not just for security, is also for something called food irradiation. Does anybody know what food irradiation is? Have you ever studied this before in middle school? No? You don't know? Good. Okay, let me explain. When you buy an apple, you know if you leave the apple after a few days, what happens to the apple?
So,
Huh? Yeah, that's right. Yeah. What? Describe what happens to the apple when you look at it. Yeah. So what word do we use in English for that?
lost.
No, simple word.
Sight.
It becomes rotten. It rots.
Rock.
Yeah. And this happens for all food, doesn't it? So if you leave a piece of meat out, after a few days, what happens to the meat? Your nice beef steak, what happens to it?
You can see the flying.
You can see it changes colours, right?
Yeah.
Why does the meat change colour or the food change colour? Well, because oxidization is one reason, but also because on the surface of the food, what lives on the surface of the food? No, what lives on the surface of the food? Yeah, bacteria. So, you're enjoying your food, but at the same time as you're eating your hamburger, please remember, as you're eating your hamburger, there's millions and millions of bacteria on the outside of your food also eating your hamburger too. Just remember that next time, okay? Now, this isn't a problem. It's not a problem when you cook your food. So when you cook your steak, then what happens to all the bacteria on the outside? It dies. Okay. But the problem is, what about before the food is cooked? Like in the supermarket, the food isn't cooked, so the bacteria is growing on it. And if it grows too much, then the food becomes bad and then they have to throw it out. So what you would like to do is you'd like to kill the bacteria on the outside. And the cobalt 60 does that. You put the cobalt 60 over the food and the radiation kills the bacteria and the insects. Don't forget the insects that live on your food. Yeah, they get killed too. No, sorry, that's not true. The bacteria is killed by the cobalt 60 and the insects can no longer have baby insects after the radiation because the radiation makes them infertile. Yes? Oh, what grows on your food? Well, for apples it's worms. I don't know actually, I just know for apples it's worms. For green vegetables like lettuce, it's snails.
Snails?
Yeah. Kiss snails.
You can eat snails.
You can, but I mean, I would prefer to cook it first. So if you're making a nice sandwich and you take off some lettuce, do you really want to be crunching into a snail that's alive? Let's talk not. Good crunchy sandwich, yeah. No, I have bought lettuce before where I have found a snail inside the lettuce.
Oh, really?
Only like about this big. Huh? I didn't eat it. Obviously I took it off. A snail? No.
I thought it's like
Sir, it's expensive.
Certain snails, yes.
Oh.
Not the snails you find in your garden. Maybe. So anyway, the cobalt 60 is great because it can clean the food. It kills the bacteria and the insects living on the food. This makes the food last longer, which makes the food cheaper, which is good for everybody. If we didn't do this, you would get quite sick from your food because every time you have some fruit or vegetables, it means there's a small chance you'll get some very bad bacteria in you. Think about your carrot in the ground. As far as you know, a fox or a rabbit could have pooed on that carrot. So it'd be good to clean the food before you eat it. So this is good for you. This radiation cleans the food for you.
And we can wash it off
What?
because like its half-life is 5 years.
No, you can't. But look, the thing is, if you had a choice between a little bit of radiation and some very, very dangerous bacteria like E. coli or stuff like this, like E. coli is terrible. Like it could put you into hospital for weeks, and in some cases it's fatal. So on a balance of which is more dangerous, potentially E. coli or the cobalt-60, really cobalt-60 radiation is much safer. Okay. So if anybody's studying food science, this is very important in modern food science. Cobalt-60 used for food irradiation. Okay, so you can see it's used for the fruit. It's used for extending shelf life, makes the food last longer, and it stops sprouts. You know sprouts? When your food starts to turn white with the little furry things on it. Yeah, those are sprouts. Little disgusting things. Yeah, okay. Did you write that down?
Yep.
Yeah, mold. Slight difference though, because we usually use the word mold for when it grows on walls, and sprouts when it grows on food. But you can call it mold as well. Yeah, it's the same thing basically.
Mold.
Okay, the last one, and this one is important for the exam, it's called carbon-14 dating. I might have talked about this briefly. Does anybody know this one? Have heard of it before?
What does it mean dating?
To
Dating.
estimate how old something is,
That's
not going on a date.
that's the thing. To find the age of that. What's the meaning? Cross something.
Yeah, fossil, yeah. How does this work? I think I was talking about this. So everybody has carbon-14 in them. Carbon-14 is radioactive. How do you get the carbon-14 in you? When you eat something, okay? So if you eat a beef burger, where did the cow get the carbon-14? From the grass. And where did the grass get it from? From the air. Because carbon-14 comes from the upper atmosphere. So it comes from the upper atmosphere, goes into plants. The animals eat the plants, and then we eat the animals and the plants. So we have carbon-14 in us, okay? So when you're dead, in 5,000 years, your carbon-14 in your body, if it's still there roughly, will be half what it was today. Every time you eat something, you keep the carbon-14 topped up. Then when you stop eating, it starts to decay. And this is how you can know how old something is, by how much carbon-14 is left. You notice it has a limit. You can't really go past 60,000 because it gets too small. Because 60,000 is like, 11, 12 half-lives. It's kind of the limit. Yeah. It's have you studied this before in middle school or high school? You think you have? It's very, very useful because when you think about it, most things that humans use used to be alive. Like for example, if we found some old papers in the ground, some old manuscript, how can we know how old it is? Well, the paper comes from what? Where do we get paper from?
Wood.
From wood, from trees, which, well, if you're talking about 60,000 years, if I said something happened 30,200 years ago, plus or minus 100 years, I think that's pretty impressive.
Makes sense.
No? Disagree? Of course you disagree. Okay. That is the last example. The two most important ones for the exam is the smoke alarm and the carbon-14. You must know those two examples, because in the exam they could say something like, give two examples of applications of radiation and explain how they work. So how does the carbon-14 work? Well, it's because we all have carbon-14 in us, we can see how much is left and work out the age. And how does the smoke alarm work? the radiation ionizes the smoke, which interrupts the current and sets the alarm off. Yeah, is that okay now? You got those two examples?
Yeah.
Yeah. Okay, so there's no homework with that, obviously, it's just pictures. So you only have one question to do for homework. Yes.
For the smoke alarm, the current decreases, then
The alarm goes off. Well, the alarm goes on if you want to use that language. You got a class at 4 o'clock? Freedom? Good.
body one. Most. Today I just need to fill in the blank. No. Red? Yeah, just one. Maybe I'll do two next time.
We need our food cooked so we don't get sick. Do you know?
Yeah.
So our digestive system has become weakened. The reason it's become weaker is because we cook our food.
Oh, so we're born with a...
No, like over generations, many years. Maybe 100,000 years ago we had a better digestive system, but by cooking the food we've weakened our system. But it has an advantage. By having a weaker system, it means we can get more nutrients from our food. You see, by having a stronger digestive system, so you can eat like moldy food, it comes at the price that you can't get as much nutrients out of it.
Thank you.